Welcome to the third video in our Class 5 series of lecture videos. In this video, we'll be discussing aromatic versus anti-aromatic system and touching on how to generate molecular orbital diagrams for these interesting systems. So let's now consider cyclobutadiene. So here we have a four-membered ring where all carbon atoms possess a p orbital. That goes into a cyclic array, a pi system of electrons. You could draw a resonance form for this cyclobutadiene where you have, the formerly single bonded carbons are now double bonded, and the formerly double bonded carbons are now single bonded. What's interesting about cyclobutadiene is it's much more reactive than, say, its analogous, big brother, cyclohexatriene or benzene. So cyclobutadiene decomposes above negative 200 degrees C. It's highly reactive, and wow, it's got 4 pi electrons, right? So you could characterize this as a 4n system of electrons where n equals 1. And what this means is it's anti-aromatic. So it has characteristics that are different than aromatic characteristics. The only common features it shares with benzene include that it's cyclic. That means you've got a ring. It's fully conjugated, so a p orbital on each carbon atom, and it's planar. So if you meet all of these three characteristics, if you're a molecule, you're cyclic, fully conjugated, and planar, then you can be characterized as either aromatic or anti-aromatic, depending on the number of electrons in your pi system. So the key difference between benzene and cyclobutadiene is the number of electrons in the pi system. So aromatic compounds are cyclic, planar, and fully conjugated with 4n plus 2 pi electrons, where n is an integer, can be 0, 1, 2, 3, etc. Anti-aromatic compounds, on the other hand, are cyclic, planar, fully conjugated with 4n pi electrons, where n is an integer. So, having covered that, how do we make molecular orbital diagrams for these cyclic polyene systems? These are called Frost diagrams by a chemist who pioneered generating them. And there are simple rules to do this. First, you inscribe the cyclic polyene ring in a circle with one vertex pointed straight down. Then you place a candle at each vertex and pray to the dark. Wait a second, that's not the rules for making molecular orbital diagrams. Let's see. Rule 2, molecular orbitals are located at each vertex. Rule 3, the center of the circle corresponds to some sort of arbitrary energy equals 0 line. So in terms of, having a bonding sort of stabilization, you would want your molecular orbitals below some sort of arbitrary energy equals 0 line. In terms of molecular orbitals that fall above that line, that would be making those electrons sort of less stable than having them in that pattern. So let's test this out, at least in a preliminary way, for the systems we've been discussing. Let's apply the Frost diagram to benzene. So we'll inscribe our 6-membered ring in a circle with one vertex pointed straight down. The center of the circle, there's a little dot in the center, corresponds to some sort of E equals 0 line. And then all of our molecular orbitals occur where vertices touch our circle. So you can see that we have 3 molecular orbitals that are below our center line, our E equals 0 line, and we have 3 molecular orbitals that are above that center line. So how many p orbitals are we bringing together when we think about, making a molecular orbital diagram for benzene? Well, we have 6 p orbitals, right? And so it makes sense that we have 6 pi molecular orbitals for our molecular orbital diagram of benzene. Just like when we had 135 hexatriene, we had 6 p orbitals and we had 6 molecular orbitals. Of course, they were linear in the pi system in terms of increasing energy. 1, 2, 3, 4, 5, 6. Here, because of the nature of how we make molecular orbital diagrams for these cyclic polyene systems, in terms of inscribing the shape in a circle with one vertex pointed straight down, and molecular orbitals occurring where each vertex touches our ring, you can see that we have a couple of pairs of molecular orbitals that occur at the same energy. When molecular orbitals occur at the same energy, we say they are degenerate, which is to say they occur at the same energy. So obviously molecular orbitals psi2 and psi3 are degenerate, just as molecular orbitals psi4 and psi5 are also degenerate. Now I think at the beginning of our next class time series of lectures, I'll go into what these molecular orbitals look like. I think it's easier to finish this video doing that exercise for cyclobutadiene. So the Frost diagram also works for anti-aromatic 4n pi electron compounds. And if we look at cyclobutadiene, what we see is a Frost diagram where we've inscribed the square in the circle, pointing one vertex straight down. But we know that our cyclobutadiene has 4 pi electrons, right? And what's interesting, what falls out of this Frost diagram is, of course, the center of the circle corresponds to some sort of E equals 0, no benefit for bonding. But you can see that psi2 and psi3, in terms of our 4 molecular orbitals, these 2 molecular orbitals are degenerate. That means they're at equivalent energies. And so when we go to fill degenerate orbitals, we fill our lowest energy molecular orbital with 2 electrons. We still have 2 other electrons in our pi system. And so we put 1 in psi2 and then 1 in psi3. And that's why cyclobutadiene is so reactive, because really it's acting like what? A diradical, right? It's not like this nice neutral compound. It's like a diradical, and radicals are really reactive, right? In terms of what these molecular orbitals look like, the lowest energy one is going to have these 4 p orbitals, one at each carbon, and the phases of the lobes are the same on the same side of the plane formed by our 4-membered ring. When we move up one step in energy, we have to add 1 node 2 different ways. So the way we do that for our 4-membered ring is we bisect these 2 carbon-carbon bonds, and then another equivalent way of adding a node is we simply bisect the 2 carbon atoms themselves. So this is what these molecular orbitals look like. You've got 1 electron in psi2, 1 electron somewhere in either of these 2 p orbital clouds, which can't really overlap with each other. And then of course when we go up another step of in energy, now we have 2 nodes, and for the cyclobutadiene at least, we have isolated like p orbitals. So cyclobutadiene is like a radical because psi2 and psi3 each have only 1 electron. And you can see from the molecular orbital diagram for benzene, we have filled molecular orbitals, right? Because we have 6 pi electrons, 2 electrons go in psi1, 2 go in psi2, 2 go in psi3, and all of these molecular orbitals are bonding in the sense that they fall below our arbitrary energy equals 0 line that helps us characterize molecular orbitals as bonding or antibonding. So that's probably enough for this video. I will see you for the 6th class time series of lecture videos.